All right. So yesterday we left with four problems. Okay, four different kind of problems which can be solved very efficiently with MapReduce. Although all of those four problems could be very well solved using any of the existing technologies, such as SQL or maybe Unix pipeline or any other custom programs. But the problem with most of those would be the one which we had discussed earlier, either the memory, CPU, or the disk read will become the bottleneck. All right, so let's continue with today's session. All right, so I want to discuss something called Hadoop streaming now. Why? Because instead of intimidating you with the Java code right now, what I want to do is I want to show you a couple of examples of doing the MapReduce with existing commands or doing the MapReduce with Python or anything. Okay, that's the reason we have kept Hadoop streaming as first before Java 1. All right. So basically, the Hadoop was written in Java, and the API, the main API of Hadoop was in Java. So we could only write MapReduce using Java as programming language earlier. And that jar which I showed you yesterday is nothing but a group of Java compiled code. Okay, it's like a zip folder. Okay, when you zip a folder, you get a .zip file. Similarly, the jar file generally contains all the things that are required to run a Java program. Okay, so so you could basically write MapReduce in Java. So some people came along. I mean, one of the developers from Hadoop, they said, let me just write some Java program which can call any other program. So they wrote a MapReduce library, okay, which has a command line argument, takes the name of your program, whatever you want to give it to, and then this MapReduce, this custom MapReduce library executes your program instead of its own logic. And that's what is Hadoop streaming. So it's a Hadoop library which makes it possible to use any binary as mapper or reducer. Okay. So what is the expectation from your program? Because this program is expecting to you to give some program which does the mapper and reducer, right? So you have to give it two programs, one mapper and other reducer. And your mapper program should give out key and value with the tab separated. Okay, so the mapper program, whatever mapper program are you using, it should give out in the on the standard output key and the value. So if you run this program with some input, it will give out key and value. This is your program. Okay, it could be any Unix command, it could be any C compiled code, it could be any Java code, it could be any Python code, it could be anything. So the mapper, the only expectation from mapper is when you run it, it should give key and the value which are separated by tab. In case this program does not give any output which contains tab, the whole so it gives some output. Your program is giving out some output which is does not contain tab. Then the whole line will be considered as the key and the value will be blank. In case there are two tabs, then all the things before the first tab will be considered as a key, and rest of the line after the first tab will be considered as the value, which means the value will contain tab. All right. So the only expectation from your program is that it should give key and value separated by tab, and this key and value pairs, I mean, there will be many key values, right? Your program is supposed to give out key and value, and those would be separated by new line. Okay, now there's a difference in the way we have understood reducer earlier. Earlier we have talked about that reducer will get key and all the values grouped together, but here in this case You'll get the sorted data instead of grouped data. Okay, meaning instead of having key space value 1 comma value 2 comma value 3 and so on, you will get key value 1, then new line, key value 2, then new line, and so on. So you will get the data, ungrouped data, as the input, and then reducer can give out anything it wants in the output. Okay, I will give some demo and then you will understand. All right, now let's take the same command which we have done earlier. Okay, so here we go. So first, when you are executing any Hadoop streaming, you have to say Hadoop, then jar, and then the name of this particular library. If in the installation you are not able to find this, what you can do is you can use this kind of a command. Okay, let me open my console so that I can show you in live. Okay, all right, so good. Now, in case you are on a computer and you don't know where is the mapper, the streaming library, if on your cluster, so you can always say name, okay, and you can say to. You can actually execute the command like this: find slash slash means find at the top folder the file with the name this, okay, and it's like in Windows you say find files. Okay, and here you could say to this dev null. Why, what does it mean? This means send the error output. If this command is encountering errors, send it to dev null. All right, meaning send it to nowhere. Okay, if you do not execute do this, then you will see so many errors. You see that? Yeah, that's why hide all the errors and see. Okay. All right, so this you can use to find the library. So we found it that this is where our Hadoop streaming library exists. Okay, now this is the library which does the magic of executing. This basically a MapReduce library which takes these arguments and execute that in place of Java MapReduce. Okay, so what does it expect? It expects input folder. Okay, this is input folder, or you can also give input file. Then the output folder should not exist before anything. And what is this slash doing at the end? This slash means that this command is spread over multiple lines. You could do something like this. Okay, just for formatting, I have kept a single command spread over multiple line. Therefore, I have put slash at the back of it. Okay, like this. Here is the important part. It means my mapper is SED. Okay, my mapper is SED. This is the command that is the mapper. What does it do? It breaks down the line, input line, into one word per line, which means since there is no tab, the value is going to be null. Okay, so the key is going to be the word and the value is going to be null. And then I am using unique minus C as the reducer. All right, in case you are confused, let me show you what exactly this individual command does. So if you say this is Sandeep, okay, and you pipe this, okay, let me just show you one step at a time. What does echo does? Echo basically prints whatever you give it on the argument on the standard output. You can pipe the output of echo to a command. And I'm just showing you that we can pipe that to SED. Okay, you can see that. So SED has replaced space with new line. And when SED is doing that, s- uh, when SED will be doing in case of Hadoop, this will be the key, is will be the key, and Sandeep will be the key, and value will be null in all these three cases, right? So whatever in data input it gets, it just breaks down into one word per line, such that the value is null and the key is there. Okay, so that's what it's going to do. And then reducer, I'm going to use unique minus c. What does unique minus c do? Unique minus c, in case there are uh, what do you say, concurrent words with the same name, okay, like for example here, then it will find the frequency. You see that? So this has occurred two times, is has occurred one, and something. The only condition with SED is that the data has to be sorted. Okay, say for example, if I do this, this is Sandeep, and then this, then it can't handle, the unique can't handle this kind of situation. Okay, therefore this is counted twice first, and then one. Okay, so unique expects the data to be sorted. Okay, so if you do sort, then it does a very good job of finding unique. Okay, so unique works on the data that is sorted, such that all the words which are supposed to be unique should occur at the together. Okay, all right, so we are able to create this command. Let me execute this command. All right, there we go. All right, what does it say? It says that it's not a valid jar. And why does it say? Okay, there is no such thing. But let's use the file which which we have found earlier. Okay, here we go. All right, let's try this. Okay, so it's saying Hadoop jar and this. It says that the output directory already exists. Okay, so what we will do is Unix, and we say 6feb. This is our command. Okay, now it says that it has created this output directory. Let's take a look at it. Okay, here you can see that there's a part 0 that has been created. Okay, all right. Now let's have a look at it. What to do if we want to see inside the data? Inside that file, we'll use the cat command, or we could simply go to Hue and use it. You can see that it has done the counts. Are you happy with the output? It has done the counts, but there are few problems. And what are those problems? You can see that. So the problem here is, you see how many times has been is there, right? Here double quote an exclamation, and so on, right? So word has been not counted properly. Similarly, for Andrew, you can see that. So we want to clean it up. Should we do it in Mapper or should we do it in Reducer? We should do it in the Mapper. Why? Why? Because if we do it in Reducer, then the sorting and grouping has already finished. So you might have to run the sorting again. Because Hadoop will do the sorting after the mapper. Whatever is the mapper's output, Hadoop will sort that output and give it to the reducer. Okay? So now, how to do that? For that, we might have to write a small shell script. It's very straight shell script. We can use a command called tr. Okay, so like for example, uh, let's say we have this is Sandeep. Okay, and I put a dot at the end of it, and I want to remove all the non-alphanumeric from this. Okay, so what will I do? I'll say substitute not A to Z, capital A to Z, or A to Z 0 to 9 with nothing. Okay, you can see that space has been substituted by nothing. Okay, so and before that we could also do things like before SED we could say translate translate the lowercase to uppercase. Okay, so we are translating lowercase to uppercase, or maybe uppercase to lowercase if we have uppercase to lowercase. Okay, so even if S is capital, it'll become the small. You can see that it has removed the space as well. Alright, now how to use this pipeline as the mapper? We will create a pipeline of the mapper. Okay, so I've already done it for you. Pico my cmd.sh or nano my cmd.sh. You can see that there is this command, and I think I have also kept this command in Hadoop fs/data. Okay, it's not there. It's not there. So never mind. I will help you with this. Okay, so we'll do that. And what's exactly happening? Let me again give you a quick demo. So the command which we are using SCD, substitute space by new line, is converting the line into one word per line. Okay, value is null and the word exists. Okay, word is the key, the SA is the key, value is null, RE is the key, and value is null, and so on. And then Hadoop is taking this data from us and converting it into an ordered one. You can see that Ga has come before Re, has come before Sa, and Sa, both the Sas have come together. And then once it has finished sorting, this is the role being played by Hadoop. Also, reading this data and executing your commands is being done by Hadoop. Okay? So unique minus C is being executed on the data which is sorted. So this is our mapper, this is our reducer, and we are getting the frequency. Okay, you can see that similar thing happens when there are multiple reducers. Okay, if there are multiple reducers, some of the keys will go to one reducer, some of the keys will go to another, and so on. In case in case there are in case your reducer is consuming too much of CPU, you generally go for multiple reducers. And please note that a single key will always go to same reducer. For example, it will never happen one SA comes here and other SA goes here. Okay? Hadoop makes sure that all the keys would go to the same reducer. Alright? So here is another example, the flow, what's happening. SCD is converting the input line into this. Hadoop is understanding it as A null, B null, C null, and so on. And then it's null basically, it's not one. And then this data is going to Hadoop and being sorted and grouped. Hadoop streaming is converting it back into this format and giving it to unique -C. Okay, so for you, it's important that whatever data you give to Hadoop, okay, is going to sort it. All right, now let's clean it up a little bit. Okay, so we'll create mycmd.sh, and what does this command do? It basically replaces space and tabs with new line And after it has done that, then it takes this output, this one word per line kind of output, and removes any alphanumeric, non-alphanumeric characters. And afterwards, it converts it into uppercase into lowercase. So this is a pipeline of command which will do the cleaning for us. Okay, this is a pipeline of command that will do the cleaning for us. And how do you do this? We basically use my nano for this. Okay, so here we have created, you can see that. So SED minus R, substitute space and tab, any number of space and tab with new line, and then substitute non-alphanumeric, anything which is not small a to z, capital A to z, 0 to 9, remove that. uh, removing means replace it with nothing, and then translate upper to lower. Okay, now once you have done that, do a chmod mycmd.sh. Okay, what I'm trying to do is I'm creating the program using shell scripting for you. In the same way, you could also create using Python or any other programming language. Okay, just that whatever program you create, it should read from a standard input and give the output in the form of key tab value to the standard output. Standard out means using printf, and standard input means scan. Okay, and also, in case you are using Python, you write this first line, which gives the definition of the program, which tells Unix that hey, my program need to be executed by this. So to test it whether your command is working or not, you should say dot slash. Dot slash means current directory. Dot means current directory. Slash means inside this directory execute my cmd. So it's reading the data from me right now. Okay, it's reading the data from me, and if I say this, okay, and say control D, it has converted and cleaned the data. Also, you can test it in this way. This is some this is some random data. Okay, this is some random data, and we are piping it to mycmd.sh. Okay, just a second. It wants me to can see that this is some random data. It has cleaned it. My CMD has converted a single line into one word per line, which means there's every line. This is basically key value pair, and value is null. This is also another key value pair where value is null, only key is there. Okay, so which means our mapper is ready to be executed. Okay, now alright, so we have written our mapper nicely, but we are not going to change our reducer. So we'll leave the reducer as such. Okay. Now this mycmd.com, there are few more things which are coming to you, and this is a real problem. Okay. This is how actually I did most of my MapReduce. Unlike the classic Java one, because classic Java is not really too much productive because you can't use these powerful tools which are already available to you. So I generally prefer using streaming job, okay, to get my all the data work done quickly. So there are many things in this command this time. So Hadoop jar up to here it's same as what we did earlier, okay, and then minus d, okay, minus d is saying that this time I want two reducer just like that. There is no special reason. Okay. And the input is here. Input is going to be in the data slash mr, and the output is going to be, let's say, in this one. I call it, okay, I'll say clean out, clean mr 6 fab. Okay, so this is what I'm trying to code right now. And also let me pick up the correct location. All right, so I'm trying to demonstrate to you that how simply you could build your mapr code without writing any single line of Java. Okay, this is very important because true engineers get their work done this way. Okay, so right now I want to first describe you that this is the total number of reducer we are describing, then this is the input folder, and then this is the output folder. This is my mapper. This time the mapper is .mycmd.sh. This command, if it is executed on h1, h2, h3, will it work? Will mycmd.sh work the way I have done just now? So this is my console. Here I'm running my cmd.sh. It is working nicely. Okay, it's expecting me to type something and then press Ctrl D. It's working fine. Do you think it will work on any other computer? It won't because it resides only on this computer. So we have to tell Hadoop that, hey, this file does not exist locally. Please take this file along with you. Okay, unlike unique, this unique command existed already on all the machines. Similarly, sed command existed on all the machine h1, h2, h3, h4. So if your program, the one which you are using in Hadoop streaming, if it does not exist on all the machines, you might have to ship it. Okay, what does it mean by shipping it? Before your Hadoop, before the task tracker does anything, it will be made this program available in the local folder. Okay, so on every node Hadoop creates a temporary folder before launching a task. Okay, this temporary folder contains this kind of files which are needed by your program. Okay, so mycmd.sh would be made available in that particular folder in which is created temporarily for executing Hadoop's job. All right, so again, this is the input folder, or you could also specify big.txt here, which is the file. Okay, but for being a little lazy, I'm just providing the folder. So it will read all the data from that folder and concatenate it, give it to Mapper. Mapper will convert it into one word per line, and then Hadoop will sort that data and give it to the reducer, and reducer will run this command on all the nodes. Okay. Now this file will be shipped to all the nodes. Okay. Before the command runs, there will be a staging area created, because when you execute a program or let's say, what does it mean by executing mapper? Executing mapper means all the arrangements will be made for a program's execution. Imagine even in Java program, you might want to connect to JDBC, or you might want to send emails, right? And for that you might want to use the libraries for sending emails. Okay, or you might want to use the library for database. So these libraries need to be copied on every node, and that's the job of Hadoop. For this, Hadoop provides something called distributed cache. Distributed cache is something, it's small files shipped to all the nodes before the program gets executed. Okay, while the input folder is read directly from HDFS, or input data is read directly from HDFS. These are the distributed cache is mainly for executing your program. This is the small data that needs to be kept on every node. Okay. All right, good. So right now we are able to successfully write this program. Let's now start executing it. Okay. So there are multiple things in this. First, multiple reducers. Second, we are creating our own program. Third, we are shipping that program. Okay. So let's try to execute this. To execute this, we need to have current correct library. If I say current, will it work? All right. I would say this. I'll say slash slash at the end of every line. I'm just putting slash so that I don't have to bring whole command into the single line. Okay. All right. Let's see what happens. Okay. Let's pay a little more attention to it. What's going on here? It's saying connecting from top to bottom. Okay, it says minus file option is deprecated. Use minus files. Yes, that's we have noted. Next time we'll take care of it. And then it says the timeline service is here. Okay, and then we have something called resource manager. Resource manager, the yarns we are talking about yarns timeline and resource manager. Okay, so resource manager basically is running at 8050 port, and then okay, we have connected to the resource manager successfully. It says that total input path is this and number of splits are 2 and so on. Okay. Now it says that the attempt has failed. For some reason, it's not working fine. There is something wrong with our reducer or mapper. Okay. All right. On some machines, it did not work correctly. But it basically first tried on one machine, then tried on another, and finally it was successful. Okay, let me see. Failed map. Oh, okay, it tried executing, but looks like okay. Okay, so job has completed successfully on two nodes. This did not work. And what is the reason for it not to work? Okay, does it want me to do anything here? Can I do current here and then try? Right, it's not a valid jar. Okay, so basically for some reason it did not work on everyone. Okay, so let's just see if this folder has been created. Clean mr6fab. Okay, clean mr6fab. All right, now this is important. You can see that there are two parts now, part 0 and part 1. Okay, earlier the output total was 1.4 MB. This time it's hardly total is 600 KB. Earlier it was 1.4. Why? Because this time the data has been cleaned and output has occurred here. Okay, so what I want to show you is this. So in part 0, you can see, let me just take these few records. Because numerics are smaller than the actual data, thereby you will see numerics first and then the actual data. You can see attic, attire, and all of that. Okay, you can see that. This time the data is perfectly clean. All right. So this time I've just taken few records from first part and few records from second part. Let me just take few records from second part. Okay, you see 005, 01, 025. This was in the first file and this is in the second file. 02, 06, 100, 124 and so on. See that? All right. Here you go. All right. So this was an introduction of MapReduce over Hadoop Stream. Moving on. Now there are a few notes which I want to go through now. All right. First is some of you already tried this. It's completely okay. It's completely okay if you don't have reducer. Okay. If you don't have reducer and you don't want sorting, then you could say minus d map reduce tasks equal to 0. Okay. Then the output of the mappers will decide the number of files. If you have multiple map tasks, it will create multiple files. And if you have single map task, then it will be creating only single file. All right. So it's okay to have no reducer. You can have things like this where there is only minus mapper, but there is no minus reducer. Okay. But the result will not be having unique. It'll be just the output of the mapper. That's it. Okay. Now question is, how many number of mappers are there? If you see, every time we execute a command, it creates some number of mappers. What does it mean? First of all, whenever you say mapper is a program, complete program. It gets instantiated. So mapper gets instantiated, and then mapper gets executed. What's the meaning of two things? Okay, instantiated means the environment for the mapper has been created, and then the map command is being executed every time. So there are two phenomena: mapper getting executed and mapper getting initialized or instantiated. Okay, so on every machine where there is a block, mapper will get instantiated only once, but the map method will be called many times. This command, the mapper command will get uh, called many times, but the environment will be initialized only once. Okay, so in case you want to force, if you want to say no, I my number of mappers should be more than one, my number of mappers should be 10, you can force number of mappers even if there is only a single block. Okay, for each block we will create something called input split. For each input split, mapper task will be initialized, and then mappers will be executed, mapper task will be executed. Okay, so the number of mappers is generally a function of number of blocks or number of input split. Number of input splits are equivalent of number of blocks in SDFS. So after reading raw data from input SDFS block, that SDFS block will be converted into something called input split, and then input split will be consumed by each mapper. So generally, the number of mappers is a function of number of input splits, but you can change it. Sometimes what happens is that your input file is very small and you want many mapper. For example, let's say you are building a distributed crawler. What does it mean? It means that you have a list of files. Say you have a million files to download, okay, or you have a million files to crawl. What you want to do is you want to divide this file into say 500 map tasks. Now, since it's just 1 million 1 million URLs, it will hardly go up to 1050 MB. Okay, that means there'll be a single block and there'll be a single map task. Now, if it's only 50 MB file and containing URLs, there'll be only a single mapper. That's not you want. You want to divide this file into say 500 mappers so that 500 mappers parallelly can download different set of websites. Correct? So in those kind of cases, you could force that my MapRed map task equals to 500. Okay, that will create those many mappers. Okay, you could say minus d mapred.map.task and these many mappers. All right. Now, a very common question is how many reducers should I use? How many reduce tasks should I create? Okay, a simple there is no simple answer. First of all, generally you discover the number of reduced tasks by doing a hit and trial. You keep on increasing number of reduced tasks from one to something, and you will hit a point where you'll get the minimum, you will get the best output, and then you can stay there. Okay, so the number of reducers, there is no single thumb rule, but still, let me go through the standard common wisdom. Okay, the common wisdom is that the total number of reduced tasks should be somewhere between 0.95 to 1.75 times the total tasks possible on your cluster. Okay, although it's just a big range. It's just a big range, a big idea. Okay, so it says that whatever task that can be executed on your cluster parallelly, multiply that with 0.95, that's your lower limit, and if you multiply that with 1.75, that's your upper limit. So choose some number of reducer between 0.95 to 1.75 times the max task. And what does it mean by task? So you go through each individual task trackers, okay, and note down how many tasks can be executed on each one. Sum it up. That means that is the ability. If you sum all the tasks that can be executed on every node, that is the ability of your cluster. Okay, that is the ability of your cluster. So by default, the task that can be executed on every node is 2. All right, and if you have 4 nodes, that means you will have 4 into 2. Your ability will be around 8. Okay, please note that if you have many reducers, your overall process will be faster, but there will be more framework load and the chances of failure will be lower. Okay, also please note that more reducers means more number of output files. Okay, all right, so far we have discussed the number of reducers and number of mappers and few nodes. We will consider more nodes as we go forward, and we'll first talk about these 4 problems which we discussed last time. Okay, the 4 problems which we discussed last time. All right, first problem was frequency of letters. For computing frequency of letters, do you need MapReduce? So without the MR approach, we could simply create an array of 26 size, scan the text character by character, and then increase A0 if we encounter A or capital A, and increase A 25th element in this array if we encounter small z or capital Z and others in between. Okay, so these are essentially 26 numbers we are maintaining. These 26 numbers represent the frequency of the letters as they occur. Okay, so the problems with this approach is RAM is not limitation. It's the network or the disk IO that will become the limitation. All right. So the approach is going to be, I'll go through a couple of approaches. Okay. So the first approach with respect to frequencies of the letter is quite straightforward. Okay. For each line, you compute the frequency of letter, and every mapper produces the output in the following way: letter and number of times that letter has occurred in the line. That's it. So every mapper is giving out the frequency it encounters for every line. Okay, and reducer at the end of it just sums it up. Okay, now question is, can we make it fast? Because if you look at it, there's a lot of data transmission happening from all of these mapper. So since every map function get executed for each line, there will be too much of data that get transmits, right? Instead, all of these mapper nodes, instead of computing line by line, they should be computing for the whole file, right? So how would you do that? So there is a way of executing reducer on every node. That's it's like local reducer. We will talk about it uh, in the next session. All right. Now the next question. This is tough. You have to find anagrams in huge text. Take the case of big.txt. Okay. So in case of big.txt, you have to find out the anagrams in the file. Okay. So what should be the key in the for the mapper? What should be the key in the mapper such that all the anagrams should come together? What is it that is common in all the anagrams of a word? So, what we will do is we will alphabetically arrange the letters of each word. So, we will take the characters of each word and then arrange it in alphabetic manner such that all the anagrams will have the same key. Say for example, we encounter the, the. What will be the key for this? What is the smallest out of all of these three letters? E, then H, and then T. So the key is E, H, T. Then we have cat. If you arrange the letters in the cat, it becomes A, C, and T. Right? Cat becomes A, C, and T. Similarly, again, we encounter act and counteract ACT. There is no change in act. Alright. Similarly, no change in IN because I is anyway less than N. So the key for in is in. For take, the key will be CIT. Why? Because C is smallest and then I, then T. Right? For take, the key would be ACT because A is smallest, then C, then T. So we are rearranging the letters. Why? Because what is anagram? All of these anagrams have just the order is different. Letters are same. So what is common in all? What is common in all? Now say they are made up of the same letters. So if we have letters in the ascending or descending order, either ascending or descending, then the total letters will be the same, and hence we will have the same key for all the anagrams of a word. You can see clearly for act, cat, and tack it is ACT, right? For tack also it is ACT as a key, and hence we will get the anagrams. All right, now the next question. So you have a big text file containing lines where each line has key and the value separated by say space. Okay, and you have to write MapReduce program such that the people with the same DNA come together. What will be the key and what will be the value? So in the input file you have been given the user ID and the DNA, and what you want to do is you want to bring the DNA people with the same DNA together. What will be the key and what will be the value? Okay, always keep in mind that when you specify key, Hadoop will always sort on the key, okay, not on the value. And that's the significance of the key. So the key will be the DNA and value will be the user. That's it. Okay. So if we have to do it using our streaming process, our mapper might look like, let's say, user 1 and DNA 1, and we give it to our say SED command, which is substitute anything, anything space, anything, okay, anything space, anything. I'm using regex extensively. Please go through regex in case you are finding it very uncomfortable. Okay, so see, I have just used SED command to generate key and the value. Okay, I've first captured my input and then substituted it like this. Okay, so this if you put this in a file, this can be your mapper. Okay, and then sorry, not this way. I'll have to put minus. Is it like this? Yes, like this. Okay, so you can see that it has switched user and DNA. It's very simple. Okay, this is equivalent of SQL equivalent, where we are trying to group by DNA, which means our key is going to be in MapReduce, key is going to be DNA, and in our aggregation it's just concatenation of the users. Okay, all right, this question is little tricky. So question this time is that some scientist came up with the idea that his research says that people with identical DNA or mirror image of DNA are belonging to the same family, or in physics term we call them isotopes. Okay, so the DNA or exact reverse DNA. So how would you bring such people together who have either same DNA or mirror image of each other? All the people in a group should be brought together from millions of such records, such that they have either identical DNA or mirror image of the DNA. Okay, so what we do here is we take the DNA and do the mirror image. So what are we trying to do? First of all, we are trying to bring all those people together whose DNA is either identical or mirror image. So if me and you have same DNA, so anyway we can group on the DNA. But if me and you have mirror image, okay, then whether we should pick my DNA or your DNA as the key, such that the result should be both. Result should be same in your case as well as in my case. The key for your DNA and my DNA should be same. How can we do that? How can we make sure that two people with mirror image have the same DNA? Okay, how can we make sure that two people with mirror image have the same key? Okay, if we just reverse my DNA and your DNA, what would happen is mine will become like yours and yours will become mine. Okay, instead, what if we pick the either the mirror image or this one, and that should be same for all. And how can we do that? If we reverse my DNA and compare my DNA and pick one of those, okay, which one of those? Let's just pick in an alphabetic order, because that's going to be same for all. Okay, so for example, let's say ACGT and TGCA. We pick ACGT because ACGT, it comes alphabetically before TGCA. Okay, comes before T and so on. So if we pick ACGT, then whether my DNA is ACGT or TGCA, the key is going to be ACGT. Had my DNA been TGCA, the key will be ACGT. Why? Because then I would be comparing min of ACGT and TGCA. Sorry, min of TGCA and ACGT. Okay, you can see that for the second user, what would happen is we will reverse TGCA and we'll be comparing min of TGCA and ACGT. So we take a user's DNA, reverse it, and compare whether reversed one or the older one is smaller. We pick the smaller one of the two. Okay, smaller as in alphabetically, which comes alphabetically before. Okay, and therefore whether it's ACGT or TGCA, the result is always going to be ACGT, and that's what I've done here. Okay, so it's a little tricky game to figure out such key that solves our problem. Okay, we are trying to utilize sorting ability such that the data which we want to bring together comes together. Here, the other thing you could have done is instead of picking the minimum one, you could have picked maximum one. Then also you would get the same answer. Or you sort the two and concatenate them together. Okay, that also is right. You will always get the same result. Okay, so for every DNA, we are going to compare the DNA with its reverse and pick the one which is smaller, because the smaller is always going to be same whether we are inversing the mirror image or the actual one. So here also, when we do the minimum of TGCA and the mirror image of TGCA, the answer is going to be ACGT, right? So this way we can form the key here. So you can see for ACGT, it's ACGT. For TGCA, it's ACGT. For ACG, it's ACG. And for ACGT, it's ACGT. Similarly here, similarly here, similarly here. Okay? To retain the actual word, we are keeping the user in the value. For user 1, we will compare ACGT with the mirror image of ACGT, which is okay, TGCA is greater than ACGT, so we'll keep ACGT in the output because we are keeping minimum. You could keep maximum, or you could keep sorted and keep it an array. That's also completely okay. All right, so what exactly are we doing here? Okay, we are using Hadoop for this. Okay, imagine that this file was really huge, such that the two users, user 1 and user 2, are in two different blocks. Okay, it's a huge file, say 100 gigabytes. Okay, and user 1 and user 2 are in two different blocks altogether. Now, even if you write a mapper which consumes the whole file, okay, you would not get the result. Reason being, mapper will be given only one line at a time. So you do not have access to the whole file, first of all. If you trick the system so that they pick up the whole data, still you will only get one block at a time. Still, you force Hadoop so to say that, okay, I have only one mapper and give me all the data. Only then you can iterate over the whole file, right? Now in that case, what would happen is, how are you going to, so Okay, so when you try to do iterative logic, you expect to go through the data by yourself multiple times, maybe, right? Pick up one DNA, compare with another, keep on going like this, and do it for all the DNAs. Now think about how many times you are going to read the data from disks. Also, you are going to do it sequentially over. If your 100 gigabyte file is located on many machines, then how are you going to do the iterative way? Therefore, generally, if you try to do it iterative way, to read the data, to read the 100 gigabyte data from a disk might take a very long time. Okay, therefore you always try to do it by a system like Hadoop. And since MapReduce tries to solve these kind of problems by using sorting algorithm, by providing you a way where you say that, hey, here is my key and here is my value, and you use that key and value technique to bring all the values for the key together. So you generally structure your problem such that you try to solve the problem by using the sorting strategies, by using group by. Okay, all right, let's discuss the problem number 4 in the next session. Okay, also there is a problem described here. The problem is, first is code MR for all the problems in your favorite language. Second is that based on a very large text archive, formulate next word recommendation. Okay, for example, happy is followed by birthday, new year, and marriage. So you get the data from say big.txt and give me the next word suggestions. Okay, all right, see you and have a great day. Bye bye.